DROWN is short for Decrypting RSA using Obsolete and Weakened encryption. It is a cross-protocol attack that allows an attacker to break a passively collected RSA key exchange for any TLS server, if the RSA keys are also used for SSL version 2, possibly on a different server. This adaptive chosen ciphertext attack is based on the Bleichenbacher attack. If you are not familiar with Bleichenbacher or PKCS 1 version 1.5 padding, watch the video about it first. SSL version 2, released in 1995, is the second version of the Secure Socket Layer protocol. The first two versions of SSL were immediately found to be vulnerable to trivial attacks, which were fixed in SSL version 3. Later versions of the standard were renamed TLS and share a similar structure to SSL version 3. The current version of the protocol is TLS 1.3. SSL version 2 still has a lot of security threats and usability flaws. Handshake messages are not protected, and there is no explicit message close. This makes SSL version 2 vulnerable to person-in-the-middle attacks. The message authentication code is also constructed poorly, which makes it vulnerable to length extension attacks. These are just some examples. Because of the inherent protocol flaws of SSL version 2, it was deprecated in 2011 by RFC 6176. Even though SSL version 2 is long deprecated and it is strongly advised not to use it, some servers will still accept SSL version 2 connections for backward compatibility. In 2016, internet-wide scans find that out of 36 million HTTPS servers, 6 million still support SSL version 2. An SSL or TLS protocol flaw consists of two phases: handshake and application data exchange. In the first phase, the communicating parties agree on cryptographic algorithms and establish shared keys. In the second phase, these keys are used to protect the confidentiality and authenticity of the transmitted application data. The handshake protocol was fundamentally redesigned in SSL version 3. This new handshake protocol was then used in later TLS versions, up to TLS 1.2. In the following, we describe the RSA-based handshake protocols used in TLS and SSL version 2, and highlight their differences. A client initiates an SSL version 2 handshake by sending a client hello message, which includes a list of cipher seeds CSC supported by the client, and a client nonce RC, termed challenge. The server responds with a server hello message, which contains a list of ciphersuit CSS supported by the server, the server certificate, and the server nonce RS, termed connection ID. The client responds with a client master key message, which specifies a ciphersuit supported by both peers and the encrypted master key. The server responds with a server verify message, consisting of the challenge RC encrypted with a session key, constructed from the master key. Both peers then exchange finished messages in order to authenticate to each other. The attack is based on the fact that SSL version 2 is vulnerable to a direct message side channel vulnerability, exposing a Bleichenbacher oracle to the attacker. This allows an attacker to deduce the validity of RSA ciphertexts, which can be used in chosen ciphertext attacks. An attacker can connect to a server multiple times with the same RSA ciphertext. If the ciphertext of the client master key is PKCS 1 version 1.5 conformant, the server responds with a message encrypted with an identical secret in server verify. If the ciphertext is not PKCS conformant, the server keys are randomly generated, and the server verify message will therefore be encrypted with a different key. The attacker first serves as a person in the middle to record TLS RSA connections. Then, the attacker converts the TLS RSA ciphertext to SSL version 2 ciphertext, and uses the earlier mentioned SSL version 2 Bleichenbacher oracle to decrypt it. The attacker thereby learns the session key for targeted TLS connections, but he does not learn the server's private RSA key. The attack works on every SSL 2.0 cipher, but it is accelerated when using export ciphersuits. These export ciphers are insecure low-grade cryptographic ciphers which were intentionally crippled to conform to US export laws in the 1990s. We consider a server accepting TLS connections from clients. The connections are established using a secure, state-of-the-art TLS and a TLS RSA cipher suite with a private key unknown to the attacker. The same RSA public key as the TLS connections is also used for SSL version 2. For simplicity, our presentation will refer to the service accepting TLS and SSL version 2 connections as the same entity. Our attacker is able to passively eavesdrop on traffic between the client and server and record RSA-based TLS traffic. He records the TLS RSA handshakes. In order to apply Bleichenbacher's attack, the attacker must transform the TLS ciphertext into a valid SSL version 2 key exchange message. Then, he performs a modified version of the Bleichenbacher attack on the server, until he is able to retrieve the session key. Note that this does not work for every ciphertext. In order to decrypt one TLS session, the attacker must passively capture about 1,000 TLS sessions using RSA key exchange, make 14,000 SSL version 2 connections to the victim server, and perform 2 to the power of 15 symmetric encryption operations. To protect against drown, servers should be configured not to allow SSL version 2 connections at all. Because certificates cost money, private keys are sometimes reused among servers. Thus, server operators also need to ensure that their private keys are not used anywhere else with server software that allows SSL version 2 connections. This includes web servers, SMTP servers, IMAP and POP servers, and any other software that supports SSL or TLS. And to make it harder for attackers to retrieve session keys, you should not allow the use of export ciphers. If you want to learn more about TLS, go ahead and visit our website at tlsacademy.cs.upb.de.